This is Dr. Elliot McGucken at 45 Surf University, and this is a brief lecture on Minkowski spacetime and what Einstein had to say about it. A lot of physicists, for whatever reason these days, remark that Minkowski's x4 is equal to ICT has little or nothing to do with general relativity, and that it actually does not work in general relativity. But they're wrong. Do not take my word for it, but heed the words of Einstein himself. I'll begin with the end of the chapter and then go to the beginning of it. Einstein, speaking on Minkowski space, states, "These inadequate remarks can give the reader only a vague notion of the important idea contributed by Minkowski. Without it, the general theory of relativity, of which the fundamental ideas are developed in the following pages, would perhaps have got no farther than its long clothes." Minkowski's work is doubtless difficult of access to anyone inexperienced in mathematics. But since it is not necessary to have a very exact grasp of this work in order to understand the fundamental ideas of either the special or general theory of relativity, I shall leave it here at present and revert to it only towards the end of Part 2. Just to repeat, without Minkowski's work, the general theory of relativity, of which the fundamental ideas are developed in the following pages, this is Einstein's book, The Special and General Theories of Relativity. Einstein states the general relativity would perhaps have got no farther than its long clothes. This is actually chapter 17 in Einstein's book, The Special and General Theory of Relativity. And here it is. Chapter 17 is a relatively brief chapter, and I will read from it. I just read you the conclusion of it, but here's how it begins. Chapter 17, Minkowski's four-dimensional space. The non-mathematician is seized by a mysterious shuddering when he hears of four-dimensional things, by a feeling not unlike that awakened by thoughts of the occult. And yet, there is no more commonplace statement than that the world in which we live is a four-dimensional space-time continuum. Einstein continues, "Space is a three-dimensional continuum. By this we mean that it is possible to describe the positions of a point at rest by means of three numbers, coordinates x, y, z, and that there is an indefinite number of points in the neighborhood of this one, the position of which can be described by coordinates such as x1, y1, z1, which may be as near as we choose to the respective values of the coordinates x, y, z of the first point. In virtue of the latter property, we speak of a continuum, and owing to the fact that there are three coordinates, we speak of it as being three-dimensional. Similarly, the world of physical phenomena, which was briefly called world by Minkowski, is naturally four-dimensional in the space-time sense, for it is composed of individual events, each of which is described by four numbers, namely three space coordinates x, y, z, and a time coordinate, the time value t. The world is in this sense also a continuum, for to every event there are many neighboring events, realized or at least thinkable, as we care to choose, the coordinates x1, y1, z1, t1, of which differ by an indefinitely small amount from those of event x, y, z, t originally considered. Though we have not been accustomed to regard the world in this sense as a four-dimensional continuum, is due to the fact that in physics, before the advent of the theory of relativity, time played a different and more independent role as compared with the space coordinates. It is for this reason that we have been in the habit of treating time as an independent continuum. As a matter of fact, according to classical mechanics, time is absolute. That is, it is independent of the position and the condition of motion of the system of coordinates. And I'm adding in here that Newton spoke of absolute space and absolute time that ticks independent of all space. And Einstein continues here. We see this expressed in the last equation of the Galilean transformation, t prime is equal to t. The four-dimensional mode of consideration of the world is natural on the theory of relativity, since according to this theory, time is robbed of its independence. This is shown by the fourth equation of the Lorentz transformation, and that is t prime is equal to t minus v over c squared times x, all divided by the square root of 1 minus v squared over c squared. Moreover, according to this equation, the time difference delta t prime of the two events with respect to k prime does not in general vanish, even when the time difference delta t prime of the same events with reference to k vanishes. Pure space distance of two events with respect to k results in time distance of the same events with respect to k prime. But the discovery of Minkowski, which was of importance for the formal development of the theory of relativity, does not lie here. It is to be found rather in the fact of his recognition that the four-dimensional space-time continuum of the theory of relativity, in its most essential formal properties, shows a pronounced relationship to the three-dimensional continuum of Euclidean geometrical space. I'm adding here, I love that Einstein goes back to the foundations and references Euclid. One of the beautiful things about Newton's Principia and Galileo's books and Copernicus's books is that they're basically written in the form of Euclidean proofs. And I think that that's something physicists have sadly gotten away from, and that a lot of insight can be gained, such as in my theory, which has the proof generally based on Euclidean logical principles that the fourth dimension is expanding relative to the three spatial dimensions at the velocity of light. Einstein continues, in order to give due prominence to this relationship, however, we must replace the usual time coordinate t by an imaginary magnitude square root of 1 times ct, or ICT, the imaginary number, ICT, proportional to it. Under these conditions, the natural laws satisfying the demands of the special theory of relativity assume mathematical forms in which the time coordinate plays exactly the same role as the three space coordinates. Formally, these four coordinates correspond exactly to the three space coordinates in Euclidean geometry. It must be clear, even to the non-mathematician, that, as a consequence of this purely formal addition to our knowledge, the theory perforce gained clearness in no mean measure. So there you have it. When you're working in special relativity, all of a sudden you find a fourth coordinate that transforms and translates much like the three spatial coordinates. I think it's interesting to point out too, a lot of people say that this Einstein speaks of imaginary time, but no, t is a real number. x4, which is equal to ICT, is imaginary, but t itself, time, is always a real number. And I think part of it is whenever you are performing calculations and an I appears, it means a perpendicularity. So I know that in more modern textbooks on relativity, instead of using x4 is equal to ICT, they use x4 is equal to CT. They drop the I, but they completely acknowledge that x4 is perpendicular to the three spatial dimensions, and it's on equal footing with the three spatial dimensions. It's perpendicular to them. Now, if you go back to Einstein's and Minkowski's time, there wasn't a wide agreement that time was a fourth dimension. That kind of appeared, and then in Minkowski's formalism, where he assigned it that coordinate x4 is equal to ICT, is a little bit redundant because it's saying we have a fourth dimension and it has the coordinate ICT. But of course that I means a perpendicularity. You know, in complex math, you can have the xy plane and the vertical axis, the y-axis, is related to I. That's mapped onto that axis, all the imaginary numbers. So basically, I think due to the historical development, they didn't view time as a fourth dimension. But then when they came across this whole idea that there's an imaginary number that's associated with the time coordinate, then that just made sense. Look, this is a fourth dimension. And actually, if you just begin with the space-time metric, basically x, y, z, and x4 is equal to ICT, that's enough to give you all of relativity right there. And it's pretty amazing. Herman Wheeler points that out in his great book, Space-Time Matter, which I'll give another lecture on. So after speaking on this, we can again repeat the comment, the conclusion of the chapter, which I opened this brief lecture with. And Einstein writes, "These inadequate remarks can give the reader only a vague notion of the important idea contributed by Minkowski. Without the idea that x4 equals ICT, the general theory of relativity, of which the fundamental ideas are developed in the following pages, would perhaps have got no farther than its long clothes. Minkowski's work is doubtless difficult of access to anyone inexperienced in mathematics, but since it is not necessary to have a very exact grasp of this work in order to understand the fundamental ideas of either the special or the general theory of relativity, I shall leave it here at present and revert to it only towards the end of part 2. So this is a great read, and Einstein actually wrote this book for more of a lay audience, but I believe different versions were published throughout his lifetime, but it's around 1920 that he's writing these words. And one of the remarkable things is, there's a lot of equations in it. And today when you read a lay book like on string theory, they argue, well, we can't show you any equations because they're too advanced and they might scare you away. I'll say just, put the equations there. But I think partially for string theory is they're not quite sure what they are. So that's kind of transformed into their method for overhyping their theories and selling books, saying, well, we would tell you about the math, but it's too advanced. That's why it's beautiful to see Einstein lays all the math and reason and logic of both special and general relativity in a book aimed at the common lay reader. Now, it is advanced, rather, but at the same time, it's good to see everything and go as far as you can and return to it time and time again and get a bit further each time. Now, my own theory is built heavily upon this, and my own theory agrees entirely with all of relativity. And basically, I looked at the equation x4 is equal to ICT, and through numerous different entries into this thought, I saw it as meaning that literally x4 moves as the time t ticks on your watch, meaning that the difference between the three spatial dimensions and the fourth dimension is that the fourth dimension is expanding at the velocity of light c. So I kind of replaced Einstein's two postulates of relativity, the first one being that the laws of physics are the same in all inertial frames, and the second one being that the velocity of light is the same for all observers. Basically, I replaced that with one simple premise or principle, and that's we live in 4 dimensions, and the fourth dimension is expanding at the rate of c, relative to the 3 spatial dimensions. And another way of seeing that is you simply look at Minkowski's x4 is equal to ICT, and you take the derivative with respect to time. So you get dx4 dt is equal to IC. And that implies that the fourth dimension is expanding at the velocity of light. Now, a beautiful thing about that is it gives a deeper underlying reason for the velocity of light. And as I stated earlier, Herman Wheeler noted that all of relativity can be derived from the space-time metric. So that whole idea, if you just envision that there's a fourth dimension expanding relative to the three spatial dimensions at the velocity of light, that right there gives you all of relativity. And then I tied into it basically how that expanding fourth dimension is also responsible for quantum non-locality, and thus the probabilities and entanglement, which are all tightly related. It's also responsible for times arrows, the fact that the fourth dimension is expanding in a direction it's not contracting. That would finally give a deeper basis for times arrows. And then the whole idea that entropy also increases, that can be traced back to the fact that we have a fourth dimension that is expanding in a unique direction and not contracting. And, you know, if you look at things as simple as Huygens principle, now Huygens is, I guess it's called the Huygens-Fresnel principle these days, but basically Huygens principle, and that's another beautiful thing that he illustrated in his book. He has that famous candle, and he says that every point on a spherical wavefront of light is a source for spherical wavefronts of light. So every point is always becoming a spherical wavefront. Now basically, I look at that Huygens principle, and that also plays a huge part in quantum mechanics and quantum electrodynamics. You'll find Huygens principle present. The idea that every point is becoming a spherically symmetrical expanding wavefront of light, which of course moves at the velocity of light. So if you take a look at that, that's pretty fascinating, because if you consider that the fourth dimension is expanding at the velocity of light and every point is becoming an expanding spherical wavefront, right there you have Huygens principle. You have an underlying mechanism for Huygens principle. So the whole idea of physics is to find, and I'll do more of this in more lectures, what the greats like Einstein and Newton and people thought about the criterion of physics, is to find fundamental or foundational principles upon which a lot of observed phenomena rest. So basically, I will treat a lot more of this in future lectures and diagrams and drawings and videos. But I've written about 5 or 6 books on it. So just look up Dr. Elliot McGucken, and I've got a Facebook page and plenty of other information out there. Just Google dx4 dt. dx4 by dt is equal to IC. That's dx4 over dt, just the derivative of x4 with respect to time, is equal to IC. Google that simple equation, and you'll be led to all of my work, as well as a lot of my photography. So enjoy that too. And this has been Dr. Elliot McGucken with 45 Surf University, and I'll look forward to seeing you soon. Bye.